Hello everyone. Please note that this is a NotebookLM video presentation. Thank you NotebookLM. Hope you find it useful.
All right, let's get right into it. We're diving into a really strange paradox in the world of AI. How is it that an AI can be a genius, smart enough to crush the world's best Go players, but then completely fall apart the second a little bit of dust gets on one of its sensors? Well, the answer, as it turns out, might be hiding in plain sight, inside the most powerful computer we know of, our own brain.
So here's our game plan for cracking this mystery. First, we're going to pinpoint the AI's critical blind spot. Then, we'll see how researchers actually built a tool to measure how confused an AI gets. After that, we'll check out a simple but brilliant trick inspired by our own biology, something like an inner clock. From there, we'll look at the master plan, an AI built like a team of specialists. And finally, we'll see it all in action, an AI that can actually adapt to our messy, unpredictable world.
Okay, let's start with clue number 1. This bizarre paradox of AI being both superhuman and, at the same time, incredibly fragile.
I mean, this is the big question, isn't it? We see all these headlines about AI mastering these incredibly complex games, becoming unbeatable. So why does that same superintelligence seem to just shatter the moment it steps out into the real world? Well, it really all comes down to the environment. Inside a game, the world is perfect for an AI. It sees the whole board, it knows every single rule, and everything is predictable. It's a clean, sterile lab. But the real world, it's messy. Data is noisy, sensors get dirty or blocked, and the universe just loves throwing curveballs. For a lot of AIs, that jump from the perfect digital world to our chaotic one is where everything just goes catastrophically wrong. So, there's a technical term for this problem. It's the main villain of our story, really. It's called partial observability. This is the AI's blind spot. It basically means the AI can never see the whole picture. And even worse, two totally different situations can look exactly the same from its limited perspective. And that confusion? That's what leads to those huge mistakes.
So, if partial observability is the problem, where do you even start to fix it? Well, as they say, you can't fix what you can't measure. So the researchers first needed a way to get a handle on just how confusing and difficult any given situation is for an AI. And what they came up with is this brilliant idea called dissonance distance. The best way to think about it is like a difficulty meter for an AI's environment. It measures how far off track an AI has to go before it falls into a trap. You know, one of those spots where two states look identical but demand completely opposite actions. So here's the bottom line. It's pretty simple. A low dissonance distance is really bad news. It means confusion and failure are just around the corner, maybe one wrong move away. A high dissonance distance, on the other hand, is great. It means the environment has a bigger margin for error, and it's much easier for the AI to figure out.
Let's make this really concrete. Just imagine this simple grid world. The AI in this world has a blind spot. It can only tell its horizontal, or x position. So when it gets to x equals 2, the world looks exactly the same to it, whether it's at y equals 1 or y equals 2. And here's the trap. In one of those spots, it gets punished for moving up, but in the other, it gets a reward. That's the conflict right there. That's the confusion.
And for this little grid, the dissonance distance is 2. That means even a perfect AI is just 2 little mistakes away from getting trapped in that confusing state. If that number were, say, 20, this world would be a much safer, much easier place for the AI to navigate.
Okay, so now we can measure the problem. So let's look at the first part of the solution. And it is such a simple and elegant trick, pulled straight from biology. It's all about giving the AI a little sense of itself.
You see, the solution isn't to bolt on more expensive cameras or sensors. It's to give the AI self-information. What the researchers did was add a simple internal oscillator. You can basically just think of it as an inner clock for the AI. It just ticks along, giving the AI a sense of its own internal time, its own rhythm.
And the power of this little clock is amazing. It adds a timestamp to every single thing the AI sees. So those two confusing states from before, they might look identical from the outside, but if the AI visits one at time step 10 and the other at time step 30, suddenly they're not the same anymore. This simple trick increases the dissonance distance, making the world less confusing, all without a single new piece of hardware. And you know what? It's a trick our own brains are using all the time.
And the results are the real aha moment. Check this out. When they tested this on the classic mountain car problem, an AI with no inner clock learned literally nothing. Its reward score was basically 0. But then, when they gave it a clock with just the right rhythm, boom!
The reward score suddenly shoots up to over 55. The problem went from impossible to solvable, all because the AI finally had that sense of time it needed to figure things out.
Now that inner clock is a fantastic hack, but is really just one piece of a bigger puzzle. The researchers thought, what if we built an entire AI architecture that was inspired by how the brain handles problems, with different parts working together? That's the master plan.
This is the spatially layered architecture, or SLA. The easiest way to think about it is like a team of specialists. Layer 1 is your fast gut instinct specialist. It only works with the bare minimum, like that inner clock. Then you have the switch network, which acts like a manager. It looks at the situation and asks, is this simple enough or do we need to call in an expert? If things are tricky, it activates layer 2, which adds more data, like velocity. If the situation is still confusing, it calls in the top expert, layer 3, which adds even more detailed data. And here's the clever part. There's a tiny penalty, like an energy cost, for using the more powerful layers. This teaches the entire system to be as efficient as possible.
The whole philosophy here is just beautiful. Use as little information as possible, but as much as is necessary. This isn't just about building an AI that gets the right answer. It's about building one that's tough, resilient, and smart about how it uses its resources.
Okay, so the theory is really elegant. A team of specialists that works together efficiently. But does it actually hold up when the pressure's on? Let's put this brain-inspired AI to the test and see what happens.
And here is the showdown. On one side, a standard AI. Watch what happens as you start taking away its senses, simulating a dirty or broken sensor. Its performance just completely collapses. It's brittle. But now look at the SDLA. Its performance just stays high and stable. It barely even notices that information is missing because it was literally designed to adapt. It just relies on its lower-level specialists that don't need that data in the first place. It is truly robust.
This team-based approach really shines on an even harder problem: balancing an inverted pendulum. If you try to use the individual layers on their own, they perform pretty poorly. But when you combine them into the full SLA system, the performance just skyrockets. The whole is so much greater than the sum of its parts. It creates what the researchers call emergent robustness, a kind of resilience that only appears when the whole team is working together.
So why does any of this matter? What's the big takeaway? Well, this research is a huge step towards AI that is truly robust. An AI that won't crash your self-driving car just because of a little rain on the camera. It's efficient. It saves power and energy by not overthinking simple problems. And ultimately, all of this makes AI far more ready for the real world, for all the complex, autonomous tech we're trying to build.
The researchers themselves put it best, really. They connect this work to a much bigger idea, saying that this ability to use precision only when you absolutely need it is the hallmark of a more advanced kind of computation, something that could lead to capabilities way beyond what we have today.
And that leaves us with this final kind of mind-bending thought. For years, the big race in AI has been about getting more data, building bigger models. But what if the real key to intelligence, not just artificial intelligence, but our own, isn't about learning to process more information, but about learning the profound wisdom of what we can safely ignore?